Welcome back to our official YouTube channel, SRN BGNR Government Degree College, Khammam. Myself, Dr. B. Satish Kumar, Assistant Professor in Biochemistry. We have been discussing about fundamentals of enzymes, that is Unit 3 in Paper 3 of BSc Biochemistry students. And in today's topic, we are going to discuss about the fourth unit, which is regulation of enzymes and inhibition. In this unit, we are going to cover topics related to regulation of enzyme activity as well as the different mechanisms of inhibition of enzymes. So far, in the previous video lesson, we have covered about the factors which are affecting the enzyme catalysis. We quickly go through these four different factors which affect the enzyme catalytic activity. First one is substrate concentration. In substrate concentration, this is one of the key factor that affect the enzyme activity, because if the substrate concentration is not adequate, then the enzyme activity will also be lower than its original capacity. So that is why the substrate concentration definitely affect the enzyme activity. So when we talk about the substrate concentration, we will have three different stages when we draw a plot uh, where we draw the plot for substrate concentration against the velocity of the enzyme. We will get three different areas. First area is the linear stage. At this stage, the concentration of the substrate and the enzyme activity both will increase proportionately, because the enzyme, when compared with the enzyme concentration, the substrate concentration is very less. So below the saturation levels of substrate concentration, the enzyme activity will be proportionally increased. So we will get a linear curve there in that region. And curve stage, so this is the stage where the concentration of substrate is approaching the saturation point. As soon as the concentration of substrate approaches saturation point, the enzyme activity gradually, the increase in the activity of the enzyme activity will gradually decrease, and it will reach to a point where the enzyme activity will be no more increased upon further increase of the substrate concentration. So that region is called unchanged stage. So unchanged stage is the stage where the substrate concentration is far more excess than the saturation point. So we will get a rectangular hyperbola. And the second factor is enzyme concentration itself. If we increase the concentration of enzyme and providing excess amount of substrate, then what happens? The enzyme activity gradually increases, proportionately increases. So we will get a straight line. And the third factor is a physical factor, that is temperature, because all enzymes are proteins in nature. They have amino acids in sequences. So these amino acids interact with each other by non-covalent interaction. So therefore, at particular temperatures, the enzyme activity will be more, and beyond that or below that optimum temperature, the enzyme activity will be decreased. So at higher temperatures, usually above 50 degrees centigrade, the proteins gets denaturation. So that is why the enzymes will also be denatured at higher temperature. So therefore, the enzyme activity decreases beyond this temperature, say for example 50 degrees centigrade for most of the enzymes. So for this we will get a bell shaped curve where the middle region is the optimum zone. It uh, it denotes that optimum range of temperature will be there for each and every different proteins or different enzymes where the enzyme activity will be at highest. So we have to discuss one important point when we consider the temperature as an factor that affect the enzyme catalysis is the temperature coefficient, which is also known as Q10. Q10 means the increase the increase in enzyme velocity when we increase the temperature by 10 degrees centigrade, it will be twofold. So that means the enzyme activity will be doubled if we increase the temperature by 10 degrees centigrade. It works in a range of temperature that is 0 to 40 degrees only. So between 0 and 40 degrees centigrade, if we increase the temperature of an enzyme reaction by 10 degrees centigrade, we will get doubled enzyme activity. So that is called Q10. Q10 is always equal to 2 in a temperature range of 0 degree to 40 degree centigrade. And another important factor is also a physical factor, which is pH, because all the amino acids in a protein or an enzyme, their charge will be affected by the pH. So each and every amino acid, so therefore each and every protein and enzyme will have one particular isoelectric point based on the pH conditions. Their net charge also changes. So therefore the activity also will be affected by the pH. So just like the temperature, pH also influences the activity of the enzyme. At optimum pH range, most of the enzymes will be active, very active at that range, and below or above that pH levels, the activity of the enzyme will drastically decrease. We have different enzymes with different optimum pH levels. Say for example, pepsin, it works only in acidic environment. So therefore, it has the optimum pH around 1 to 2 pH only. Below 1 or above 2 pH, the activity of the pepsin will gradually decreases. Acid phosphatases, optimum pH 4 to 5, and alkaline phosphatase, it has 10 to 11 pH as optimum pH. Then we have moved on to the chemical kinetics topic, where we have to learn the equation which is derived by Michaelis-Menten, and it is also known as Michaelis-Menten equation, which goes as V equal to V max S by Km plus S. V, it is the initial velocity of the reaction. V max equal to maximum velocity of the enzyme where excess substrate has been used, and S is the substrate concentration, and Km is the Michaelis-Menten constant. So for the derivation of Michaelis-Menten equation, we have to keep three important points in mind. The first one is we have to understand the enzymatic uh, reaction. Enzyme interacts with the substrate and forms the enzyme substrate complex, and this complex either it can move forward and form product and enzyme, or sometimes it may move backward and the substrate may dissociate without entering the catalytic reaction. So this the reaction where the product is formed from enzyme substrate complex the key reaction stage, which is the rate limiting step, slower one and rate limiting step. So therefore, the velocity of the enzyme always depends on the reactant, concentration of the reactant, that is enzyme substrate complex, concentration of enzyme substrate complex, and at the same time its rate constant, which is K2, which is K2 in this case. So V equal to K2 ES. So this is known as law of mass action. And very important thing to consider here is the the steady state assumption. The steady state assumption explains that the concentration of enzyme substrate complex will be at a steady state for most part of the enzymatic reaction. It will not be changed during the course of the enzyme reaction. So that means the formation of ES and dissociation of ES will be same. So therefore we can write it like the formation is equal to dissociation of ES. So putting all these things together, we will get these following mathematical expressions. And another more important thing is the total enzyme concentration which we have used in the reaction will be equal to the free enzyme which is unbound state, plus the enzyme which is in bound state. So when we combine the unbound plus bound forms, we will get total enzyme. So we can measure the total enzyme concentration, but we cannot measure directly what is the free enzyme concentration and what is ES, enzyme substrate complex concentration. So now putting all these things together, we will solve for ES, the ES concentration. So by following all mathematical expressions and deriving and simplifying the total variables and equation, we will get finally our Michaelis-Menten equation, which is nothing but V equal to V max S by Km plus S. Here Km is the Michaelis-Menten constant. So now the velocity, the initial velocity of the reaction is equal to V max S by Km plus S. So we know the substrate concentration which we are adding to enzymatic reaction, and we can find out the Vmax also. We can also measure the Vmax, because at very excessive amount of substrate concentration, the enzyme will have Vmax. Enzyme will get Vmax. So we can measure the Vmax also easily, either from plot actually from the by plotting velocity of the enzymatic reaction against its concentration. We can easily calculate what is Vmax. So we have Vmax to calculate the velocity of the reaction, but we don't know what is Km, what is the value of Km for a particular enzyme. So to measure the Km value, we can have one method where we can say that if the velocity of the enzymatic reaction is equal to half maximum, then what happens? So that means if we assume V equal to 1 by 2 of Vmax, so then what happens? So if we substitute V equal to 1 by 2 Vmax in this Michaelis-Menten equation, we will get 1 by 2 Vmax equal to Vmax S by Km plus S, and then we are moving the two digit uh, to right hand side, we will get Km plus S equal to Vmax S by Vmax, and just Km plus S, we have taken uh, this word these two variables into left hand side, and finally we will get Km equal to S. So then what does it mean? It means Km is equal to the concentration of substrate. So that means Km is defined as the velocity of the substrate concentration, the concentration of the substrate at which the velocity of the enzymatic reaction is equal to of maximum velocity. In other words, simply we can say that at which substrate concentration level the total 50% of the enzyme molecules are bound by substrate molecules. So suppose if we have suppose if we have 100 enzyme molecules, and suppose if we use 100 substrate molecules for a particular enzyme. In this case, only suppose out of 100 enzyme molecules, we have 30 enzyme molecules bound with substrate, and remaining 70 are free at 100 substrate molecules. So that means the enzyme is binding only 30 molecules out of 100 substrate molecules, and 70 enzymes are free. So if we increase the concentration of substrate, suppose by up to 200, if we add 200 substrate molecules, then in this case now the enzyme binds 50 substrate molecules only, and 50 enzymes will be free. So out of 100 we have 50 enzyme molecules which are bound by substrate molecules. At what concentration? At 200 concentration. So this 200 concentration, 200 units of concentration is the concentration at which the 50% of enzyme is bound by substrate. So this is known as Km for this particular enzyme. So Km is the substrate concentration where 50% of the enzyme molecules, enzyme active sites are occupied by substrate. So that is equal to of maximum velocity. So here we can see that this is the normal plot where we draw the plot for rate of the enzymatic reaction versus substrate. So in this case, the substrate concentration is gradually increasing, and so the enzyme velocity is also increasing. At a particular point where the substrate concentration increases beyond the saturation level, we will get the maximum velocity of the enzyme, which is known as Vmax. So Vmax is here. So here Vmax, and 50% of the Vmax is this. So at 50% of Vmax, if we draw a line from 50% to this curve, and draw this line to x-axis, then we will get a substrate concentration here. This substrate concentration is equal to Km. So Km is the substrate, this Km is the substrate concentration at which the velocity of the enzyme reaction is equal to of maximum. So using this substrate saturation curve, we can find out what is Km value for a particular enzyme. For each and every enzyme, a separate Km value will be there. And here, one drawback is there while using substrate saturation curve, that the curve is not at all straight. So therefore, it is not accurate. We cannot measure the Km value accurately by using this curve. So therefore, to find out the accurate value of Km value of an enzyme, we will use another different approach where we convert the we take the reciprocals of Michaelis-Menten equation. Reciprocals means, so we divide everything by 1. So for V we will have 1 by V and V max S by Km plus S. So if we write 1 by V max S by Km plus S, so then it becomes Km plus S by V max S. V max S comes down and Km plus S goes to the top. So if we solve the equation for this, we will get an equation which is similar to y equal to mx plus c form. So y equal to mx plus c is the equation for a straight line. So that means if we take reciprocals of all the variables which are used in Michaelis-Menten equation, we will always get a straight line which is equal to y equal to mx plus c. So this is known as Lineweaver-Burk double reciprocal plot. This is also known as LB plot. So by using LB plot, we can accurately measure the Km value. Instead of getting a rectangular hyperbola, we will get a straight line. Here on x-axis, instead of S, in case of substrate saturation curve in this LB plot, we will use 1 by S. We will use 1 by S on x-axis and 1 by V on y-axis. By taking these reciprocals and substituting all the values, by gradually increasing the substrate concentration levels, we will get a straight line which is similar to the y equal to mx plus c form. So therefore, from this straight line we can easily calculate. In y equal to mx c, y means the value on y-axis and x means the value on the x and c is the intercept. By comparing these values, we can easily get the Km value here. Okay, this Km value that we are getting on x-axis intercept, the line will intercept the x-axis at this point where we will get minus 1 by Km value. So from this we can easily calculate the Km value. Now that Km value will be more accurate, which more accurate than that is calculated from substrate concentration saturation curve which is used earlier. Okay. Therefore, we can easily calculate the Km value with more accuracy, and we can calculate the Vmax value here, and from the slope we can calculate Km by Vmax value also. So this is called LB plot, which is used to accurately measure the Km value, and which is also very useful in studying the enzyme kinetics and enzyme inhibition as well. next topic in this Unit 4 is enzyme inhibition. How the enzymes are inhibited and what are the different kinds of inhibition mechanisms for different enzymes. So far, we have three different enzyme inhibition mechanisms. Enzyme inhibitions are broadly categorized into three broad categories. First one is reversible inhibition, second one is irreversible inhibition, and third one is allosteric inhibition. To start with, the first one is the reversible inhibition. Before that, we are going to discuss about what is an inhibitor. Inhibitor is a molecule or a substance which inhibit the activity of the enzyme. Substrate finds the active site and bind and forms the product, but enzyme sorry the inhibitor that also binds the enzyme molecule and inhibits its activity, so the enzyme will no longer work to catalyze the enzymatic reaction. So inhibitor which inhibits the enzymatic activity, so that the inhibitor either it may bind to substrate binding site or somewhere else. In either cases, that will inhibit the enzyme activity. So first one is the reversible inhibition. In case of reversible inhibition, that means the binding and inhibition of enzyme activity is reversible. If the inhibitor binds the enzyme will be inhibited. And at the same time, if the inhibitor is released from the enzyme, once again the enzyme starts its activity. So this is called reversible inhibition. It binds for some time, and when we change the conditions, it also releases from the enzyme. So that is why it is called reversible enzyme inhibition. So why the inhibitor easily binds and comes out of enzyme means, like substrate, here the inhibitor also binds the enzyme with non-covalent interactions. So that is why the interaction between enzyme and the inhibitor is very weak. So therefore, if the inhibitor binds, enzyme will be inhibited. If the inhibitor is released from the enzyme, then enzyme once again will be active. So therefore, the interaction between enzyme and its irreversible inhibitor is by non-covalent interactions. This reversible inhibition is also subdivided into two more categories. First one is competitive inhibition and second one is non-competitive inhibition. So the competitive inhibition, the name itself explains that the inhibitor will compete with the substrate molecule for the active site. That means the inhibitor resembles the structure of its substrate. So both substrate as well as inhibitor will be in similar structure. Therefore, the inhibitor will compete with the substrate to bind to the active site of the enzyme. This is called competitive inhibition. The important things to consider here is both the substrate and inhibitor will be structurally similar. Both will compete for the same active site. If the concentration of substrate is more, then substrate binds more. If the concentration of inhibitor is more, then inhibitor binds to active site more than the substrate. So it depends on the relative concentration of the substrate and as well as the inhibitor. So therefore, If we add excess inhibitor, then enzyme will be inhibited. If we increase the concentration of substrate, then once again the enzyme will be active. That is why it comes under irreversible inhibition. And as the inhibitor is competing with the substrate for the same active site, it is called competitive inhibition. Here we can see that enzyme, if we add substrate, we will get Es, and from Es we will get E plus P. Product will be formed. Otherwise, if we add I inhibitor, we will get EI complex, which is an inactive complex. A product cannot be formed from this. Okay, here also we can see that this is the enzyme. We have active site. This active site, it binds substrate to form enzyme substrate complex, or otherwise sometimes if we add excess amount of inhibitor, it binds the inhibitor and forms EI complex. So both substrate as well as inhibitor are competing for the active site, and both are structurally similar. And when we study the kinetics of competitive inhibition, so here we will get that the Km value increases. The Km value of enzyme increases in presence of inhibitor, but the Vmax will remain unchanged. Okay, so because Km value, it is the property of active site. So because the substrate and inhibitor both are competing for the same active site, then more substrate concentration will be required to saturate 50% of the enzyme molecule. So therefore the Km value increases. So if we add more and more inhibitor molecules, the Km value also changes for the enzyme. But the Vmax never changes, because Vmax is the velocity of the enzymatic reaction where excess amount of substrate concentration will be used. At excess amount of substrate concentration, the concentration of inhibitor will be negligible. So therefore the inhibitor cannot affect the enzyme activity. So that is why in a competitive inhibition, Km value increases but Vmax remains unchanged. In this video lesson, earlier we have discussed about the Km value. One point I forgot to mention is the Km value will also be known as affinity of the enzyme. If the affinity of the enzyme affinity of the enzyme, the low Km value indicates strong affinity between enzyme and substrate, whereas high Km value reflects a weak affinity between them. So that means at low Km value means low substrate concentration. At low substrate concentration also, the velocity of the enzymatic reaction is reaching of maximum velocity. So that means the affinity between the enzyme and substrate is high, and vice versa. Therefore the Km value indicates the affinity between enzyme and substrate. So it is the property of enzyme sub and enzyme's active site and the substrate. So active site property. So if the affinity is more, then that means the Km value is less. If the Km value is high, then the affinity is less. One particular example for competitive inhibition is substrate dehydrogenase, which is succinate dehydrogenase, which is an enzyme of TCA cycle. And in fact, the succinate dehydrogenase that will form succinate to fumarate. But instead of succinate, sometimes uh, it may bind malonic acid, glutaric acid, and oxalic acid. These are all these three malonic acid, glutaric acid, and oxalic acid are structurally similar with the succinic acid, but the enzyme cannot catalyze the dehydrogenation reaction. So therefore, once one of these three uh, molecules binds to SDH, they act as inhibitor and stop the reaction. And the second one is non-competitive inhibition. Non-competitive inhibition means there is no competition between substrate and inhibitor for the enzyme's active site. So that means the inhibitor binds other than the active site. So it will not bind to the active site and somewhere else on the enzyme. It binds somewhere else on the enzyme. So therefore, the enzyme inhibitor for that enzyme, the non-competitive inhibitor will have different structure compared with the substrate structure because that is not binding to the active site. Here in this reaction we expression we can see that enzyme interacting with substrate, enzyme interacting with substrate, ES complex and E plus B. Okay, and now the inhibitor can directly bind to the free enzyme or it can bind to the ES complex also, because the place of binding of inhibitor is different from the active site. So that is why it can either it can bind to free enzyme or it can also bind to ES complex. Okay, if it binds to free enzyme it gives EI complex, or if it binds to ES complex it gives EIS. in in both the cases the enzyme will be inhibited, whether the substrate is there or not. It doesn't compete with that and it strictly binds its own site on the enzyme. Therefore the Km value is unchanged because the active site will only be bound by substrate, not the inhibitor. So the Km value is unchanged, but the Vmax is lowered because the inhibitor concentration will affect the velocity of the enzymatic reaction. There is there is no competition between the substrate and inhibitor. So therefore, a small quantity of inhibitor also decreases the Vmax value. So therefore, the Km value is unchanged and Vmax is lowered. For this, we have one specific example where these heavy metal ions acts as non-competitive inhibitors. So mercury is one such metal ion which binds to the sulfhydryl group of enzyme, which is not present in the active site, and due to the binding of this mercury ion the enzyme conformation changes a little bit and activity will be affected. So this is an example of non-competitive inhibition. So far we have discussed about the enzyme inhibition processes. In the beginning of this video lesson, we have discussed about how to calculate the Km value, what is Km value and how to calculate the Km value. For that, we have to use LB plot to accurately measure the Km value. Km value is nothing but the affinity of the enzyme towards the substrate. If Km is more, affinity is less. If Km is less, affinity is more. By using LB plot, we can accurately measure Km value and as well as Vmax value also. And in the topic of enzyme inhibition, we have three different categories of inhibition: reversible, irreversible, and allosteric inhibition. So far we have discussed about reversible inhibition, and in the reversible inhibition we have two subcategories: competitive and non-competitive inhibition. In the reversible inhibition, uh, the interaction between inhibitor and enzyme is by non-covalent interaction. So therefore it is reversible. Inhibitor irreversibly binds to the enzymes and inhibit the activity. Competitive inhibition means the inhibitor binds to active site and competes with the substrate. Therefore the Km value changes, Km value increases without change, changing the Vmax value. And in non-competitive inhibition, the inhibitor binds other than the active site, therefore Km is unchanged but Vmax will be lowered. And in the next class we will discuss about the irreversible inhibition. Thank you.